本日最後の講演となりました。最後の講演はベンナッシさんからのご講演で、タイトルはLamphone、電球の振動からリアルタイムな受動的音声復元についてお話しいただきます。ベンさんはイスラエル在住の学生で元 Google 社員でいらっしゃいます。Lamphoneは非常に話題になった発表で、電球の振動から盗聴ができるというまるでスパイ映画のような内容になっています。今回のテーマにつきまして動画をいただいております。Our next session is Lamphone, real-time passive sound recovery from light bulb vibrations. Sorry. Please welcome our speaker, Ben Nashi.
Hello, Code Blue, and welcome to my talk, Lamphone, real-time passive sound recovery using light emitted from a hanging bulb. And let me start by introducing myself. My name is Ben. I'm a computer scientist and a former Google employee. I'm a PhD student at Ben-Gurion University of the Negev and a researcher at Cyber BGU. My research focuses on security and privacy of IoT devices, and you can read more about my research at my website. This is a joint work made with the help of Yaron Pirotin, Professor Adi Shamir, Professor Yuval Alovich, and Dr. Boris Zadov, all of us from Ben-Gurion University and Weizmann Institute of Science. Let's review the agenda for today, and we will start by discussing the research question. We will then continue to understand the necessary background to understand how Lamphone actually operates. We will continue by discussing Lamphone's threat model, and we will then analyze how bulbs can be used as microphones. I will continue by showing you the evaluation from the experiments that we did. We will discuss about potential improvements. We will discuss about the primary takeaway from this research, and at the end will be the Q&A. Okay, so the first question that I want to ask you is, can a hanging bulb be used as a microphone? And my answer to you is, by using scientific tools to analyze the vibrations of a hanging bulb, attackers or eavesdroppers can recover high-quality speech and non-speech audio. And I will start with a warning. Turning a hanging light bulb into a microphone is very challenging, and probably some of you are asking yourself why. And the primary reason is because light bulbs were not exactly designed to be used as microphones. So during the next 30 minutes, I will try to convince you that hackers can exploit the vibrations of a hanging light bulb and turn it to a microphone if they know what to look for. Okay, the background. And let's start with the understanding what the sound wave is. And a sound wave is air traveling through space. The source is some object that causes a vibration, for example, a person's vocal cords. And acoustic waves that have frequencies from around 20 hertz to 20 kilohertz can be heard by humans. Now, eavesdropping is the act of secretly recovering sound from a target victim or a target or from any target without his consent. This is, by the way, a definition taken from Wikipedia. And eavesdropping can be performed digitally and physically. And in this research, we actually focus on a physical method to apply eavesdropping. And physical eavesdropping relies on objects that are located in physical proximity to the sound source. And when a sound wave hits the surface of an object, causes the object to vibrate. And by analyzing the object's response to sound, the vibrations, with a proper device or a sensor, sound can be recovered. Okay, so let's understand how microphones work. And microphones are devices that are used to convert sound waves to electrical signals, and they rely on the three next primary components. The first component is a diaphragm, which is a thin piece of material that vibrates when it is struck by sound waves. The second component is a transducer, which is used to convert a diaphragm's vibrations to a current. And the last component is A to D, which is used to sample the analog electric signal at standard audio samples, at the standard audio sample rates. And in recent years, the scientific community has suggested various ways to recover sound, and all of the methods basically can be categorized into one of the two next categories. The first category is internal methods, and the second category is external methods. And let's understand the differences between them. Internal methods are methods that rely on data obtained by a device located in physical proximity to a victim. And recent studies have demonstrated that motion sensors that are integrated to smartphones and speakers and even vibration motors, all of which are integrated to smartphone nowadays, can be used to recover sound. And from the eavesdropper perspective, these methods are permissionless, which means that applications that implement these methods do not require any permissions to obtain data from the devices. However, such methods require the attacker to place a malware or to compromise the device that is located near a victim, for example, a smartphone, in order to obtain the data and to exfiltrate the data. So this is a great disadvantage of such methods. Now, external methods are the second category of studies in this area. And these are methods that rely on data obtained by a device that is not located near a victim. And one good example is the laser microphone, which uses a laser transceiver to recover sound by directing a laser beam at an object and analyzing the object response to sound. And from the eavesdropper perspective, this method is external, which means that it doesn't require the eavesdropper to place a malware or to compromise a device that is located near the victim. And also this method can be applied in real time. However, this method's greatest disadvantage is the fact that it is active. The laser beam can be detected by victims by using a dedicated optical sensor that detects the laser beam that is used. And the second method in this category of external methods is the visual microphone. Now, the visual microphone introduced 6 years ago by a group of scientists from MIT. They showed that high-frequency video camera can be used to recover sound by analyzing the object response to sound. They showed that a bag of chips, for example, can be used to recover speech. And from the eavesdropper perspective, this method's greatest advantage are the fact that this method is external. Again, it doesn't require the attackers to compromise the device that is located near a victim. Also, as opposed to the laser microphone, this method is passive, which make its detection very difficult for victims or for organizations. However, this method's greatest disadvantage is the fact that it cannot be applied in real time because it requires heavy computational resources. It takes a few hours to recover a few seconds of sound. Okay, let's summarize the section of the related work. As I mentioned before, there are two categories, the internal methods and the external methods. And from the eavesdropper perspective, each method is limited by one of the following characteristics. Some relies on remotely controlled device, which require the attacker to, require the eavesdropper to compromise the device with a malware device that's located near the victim. Another disadvantage is the fact that some are active, which makes it easier for the victim to detect the use of the method. And some cannot be applied in real time because the method requires heavy computational resources. Now let's review Lamphone's threat model. And Lamphone is a method to recover sound by analyzing the vibration of a hanging bulb with electro-optical sensor. And we assume that the hanging light bulb exists in a target room or a target organization. And a sound in the room, which can be the result of a conversation, creates fluctuations on the surface of the hanging bulb and actually turn it to a diaphragm. Now the eavesdropper directs an electro-optical sensor at the hanging bulb via a telescope, and as a result, the diaphragm now turned into a transducer. The optical signal is sampled from the electro-optical sensor via an A to D and processed using a dedicated sound recovery algorithm into acoustic signal. Now, from an eavesdropper perspective, Lamphone's threat model is external, passive, and as I will show you in a few slides, it can also be applied in real time. Now let's review let's analyze how light bulbs can be used as microphones. And as I mentioned before, sound wave is air traveling through space. The air causes a hanging light bulb to vibrate. However, a bulb's vibrations are so small that they are invisible to the human eye. So the first question that we try to answer is, how small are these vibrations? Now, in order to answer this question, we actually conduct an experiment. We attached a gyroscope to the bottom of a hanging bulb, and we produced various sound waves at different volumes, at 3 levels of volumes from the speakers. You can see them to the right. And we sampled the gyroscope at 800 Hertz using Raspberry Pi 3. Again, you can see the Raspberry Pi at the bottom. Now, here are the results. We computed the angle as the function of the frequency. And when I say the frequency, I mean the sine wave that was played for phi and for theta. And you can see phi and theta on the scheme to the left. And we analyzed the results, and we actually concluded the following regarding the angle of vibrations. The angle of vibration is very small. It is in milli-degrees, as you can see in the features at the bottom. As you can see, the angle of vibration is not equal. It changes as a function of the frequency. And another insight, an unsurprising insight, is that the angle of vibration increases as the volume increases. You can see it again in the picture below. So based on the known formula of the spherical coordinate system, we computed the total movement, taking into account phi, theta, and the distance between the ceiling and the bottom of the hanging bulb. And these are the results that were obtained. Sound affected the hanging bulb, causing it to vibrate at 300 microns to 950 microns between the range, the region of the range. You can see it at the picture to the right. Now, we actually tried to answer another question. Can we detect the movement of microns by using an electro-optical sensor? So in order to answer it, we actually conduct another experiment where we try to, we actually directed an electro-optical sensor toward a hanging light bulb when it was illuminated. And we measured the voltage that was produced by the electro-optical sensor from various distances, from 1 meter to 9.5 meters. And the graph to the right show you the results. A different amount of voltage is produced by the electro-optical sensor when the sensor is placed. You can see, for example, at 2 meters and at 6 meters. You can see that the amount of voltage increases as a result of the fact that light deteriorates with distance. And this is probably the best time to indicate, to know that this is good results. However, we are interested in measuring small movements of the bulb rather than large movements of the sensors, of the sensor. And another question that we try to ask is, how can the amount of light expected for displacement of microns be computed from this experiment? So in order to answer it, we actually did the following process. We computed linear equations between 2 consecutive points on the graph. You can see the graph to the right. This graph was was created in the previous experiment. And you can see the linear equations below. And based on the linear equations, we computed the expected voltage resulting from displacement of 300 microns and 950 microns. And you can see the expected voltage difference at the right. And in order to set a criteria, we first try to understand what level of sensitivity can, for example, 16-bit A2D provide. And we computed the sensitivity of the 16-bit as follows. A 16-bit A2D provides a sensitivity of 300 microvolts. You can see the computation here. And the first conclusion that we made from this observation is that a sensitivity of 300 microvolts is sufficient to recover the entire measured spectrum from, for example, a distance of 2.5 meters. And this is because the smallest vibration that's expected in this range produces a difference of 300 microvolts, which is actually the sensitivity of 16-bit A2D that we used in our experiment. However, another interesting conclusion that we made is that in order to detect a bulb's vibration from a greater distance, the sensitivity of the system needs to be increased, or the signal obtained needs to be amplified. And at the end of the talk, I will discuss and I will explain how each of which can actually be satisfied. Okay, so I want to show you the evaluation from the results from the experiment that we did. And this is the experimental setup. We evaluated Lamphone's performance for recovering sound from a bridge located 25 meters from an office. You can see the bridge and you can see the office in the picture below. And the office contains a 12-watt E27 hanging light bulb. And I want to show you the experimental setup in a video. Okay, so the sound that was played inside the office cannot be heard from the bridge. The bridge is located on top of a rail station, and there is a great ambient noise. And the first experiment that we did is we tried to characterize the baseline, and we conducted an experiment when we obtained optical measurements via the electro-optical sensor when no sound was played in the office. And these are the results. We found that the LED bulb, which works at the LED bulb works at 100 hertz, and we found that there are peaks as a result on the FFT graph at each of the harmonics at 200 hertz, at 300 hertz, etc. And the first conclusion that we made is that we need to filter this noise with bandstop filters because this is a side effect and this is not the result of sound. Also, we found that there is noise at low frequencies. You can see it in here at below 50 hertz. This is the result, by the way, of the natural vibration of the bridge, which is located on top of a rail station. And we concluded that we need to filter this noise with a high-pass filter. And these are the conclusions that we made from this experiment. Now, the second experiment that we did is we tried to analyze the frequency response, and we did the following experiment. We actually obtained optical measurements via the electro-optical sensor when a frequency scan was played via speakers in proximity to the hanging bulb. And we actually obtained the optical measurements via 3 telescopes with the a telescope with the 10 centimeter lens with the 10 centimeter lens, 20 centimeter lens, and 35 centimeter lens. And first we found that the signal to noise ratio improves when a telescope with a bigger lens is used. I will explain it in a few slides from now, the reason for this result. And the second conclusion that we also made, and you can see it again at the figure at the left, is that the signal to noise ratio is not equal across the spectrum. And we actually conclude that an equalizer needs to be applied in order to balance the frequency response of the recovered signal. You can see the equalizer that was used in the rest of the experiment to the right. Okay, so we started by testing the performance of Lamphone at the task of recovering non-speech audio. And we actually conducted an experiment where we played two famous songs inside the office. The first song is Let It Be by the Beatles, and the second song is Clocks by Coldplay. And we obtained the optical measurements and we recovered the signals. And you can see here the spectrograms of the raw signal at the left, to the left, the recovered signal in the middle, and the original signal on the right. And for many of you, the spectrograms are nice, but they're not saying a lot. So let me play you the recovered audio. And we actually Shazammed the recovered signals, and I'm about to show you that the recovered signals are in high quality and they are both recognized by Shazam. As you can see from both videos, both the recovered non-speech audio is in high quality and they are both recognized by Shazam. Okay, so we continue to test the performance of Lamphone on the task of recovering speech audio, and we actually conduct another experiment where we played a famous statement made by Donald Trump: "We will make America great again." We obtained the optical measurements and we recovered the signals. And again, the raw signal, the optical signal, you can see the spectrogram on the left side. The recovered signal is is in the middle, and the original signal is on the right side. And we actually investigated whether the recovered signal could be transcribed by Google's speech-to-text engine. And I want to play to you and show you that Google's speech-to-text engine was able to transcribe the sentence correctly.
We will make America great again.
So as you can see, I think that many of you were able to hear President Trump and understand what exactly he says. And also, as you can see, Google was able to transcribe President Trump correctly. Okay, so I want us to understand the potential improvements that attackers can employ to this method. And first of all, as I showed you before, using a telescope with a larger lens diameter actually improves the signal-to-noise ratio. And this is because more amount of light is being captured by the electro sensor, so improves the signal-to-noise ratio. Another potential improvement is to use a better or more sensitive electro-optical sensor than the one that we used in our experiments. Or, for example, use multiple electro-optical sensor for multi-channel audio recovery, which is a common approach in audio processing. Another improvement is to use an A2D with a lower noise level, or to use a more sensitive A2D than the one that we used in our experiments. And another improvement that can be employed is to use some more complex filtering techniques to filter the noise. We actually use some very simple methods in our to recover sound, and there are great new algorithms that provide new techniques and some advanced techniques to filter noise from signal. For example, deep learning is only one of them. Okay, so the primary takeaway that I want you to take from this talk is that it is now 2020, but I want you to mark 2026 on your calendars, and some of you are probably asking yourself why, and I want us to examine Gyrophone scientific progress in order to explain to you in order to answer the question of why. And Gyrophone, for many of you, it doesn't say a lot, but at 2014, the attack vector of eavesdropping via motion sensor was revealed. And it was revealed by a group of scientists from Stanford, and they named it Gyrophone. And they basically, back then, suggested a classification model to classify isolated words that yields results which are only slightly better than a random guess. And also the attack vector of Gyrophone relied on speech at the high volume, as in the case of Lamphone. And if I would have to place Gyrophone on the scale of non-practical to highly practical, I would consider Gyrophone as, back then, 6 years ago, as not practical. And mainly this is because of the two reasons that I just mentioned. However, during the next years, an increased understanding regarding this attack vector was gained, and the accuracy of the classification model improved significantly, and some better understanding regarding the experimental setup was gained. And this was thanks to two other studies that were conducted between 2015 to 2018. And this year, the attack vector was improved to make it a real and practical threat to privacy. A recent study from NDSS was able to present, to optimize this method and presented a classification model with excellent accuracy. And also the attack vector is now relies on speech at the normal volume. So analyzing the scientific progress that Gyrophone made through the last 6 years, we actually conclude that it took scientists 6 years to improve Gyrophone to the point that it now poses a real threat to privacy. And my forecast is that by 2026, scientists will improve Lamphone, so it will also pose a real threat to privacy. And in my opinion, Lamphone is somewhere in the middle between non-practical to highly practical, and it's basically an evolution of a visual microphone. However, I do believe that somewhere in the next maybe 2 or 3 years, you will find out, or you will hear about another research that was able to recover sound from light, and they were probably going to be able to show it or to demonstrate it with lower sound level. And this is it. This is the primary takeaway that I want you to think of from this talk. So I want to thank you for attending this talk. You can find more information about this research if you will scan the QR code to the right. You can also find the link to the paper in the QR if you will scan the QR code. And let's start the Q&A. Once again, thank you all for attending this talk.